The last two ingredients to compute Buchberger's algorithm are the S polynomial and the list of the pairs. So let's start from the S polynomial, which will show us some new features in CoCoALib. So an S polynomial uses for input two polynomials, G and H, and returns a polynomial. So it's a ring element. And we do these operations. First of all, I need to know the ring. We will see it in a moment why. And this time I will use a clean function, so I don't need not a pointer function, so I don't need to specify it is a sparse polyring. So P is the ring of one of the two polynomials. Then I have the function, the same line that I had in CoCoA5, which is I create the element, which is the least common multiple of the LPP of G and the LPP of H. Here you have a surprise. A surprise is that the result is a PP monoid LM. In CoCoALib, in fact, we have a more refined data types like monoid elements. So we can have something that is X, Y, and Z, and I can multiply by Z squared as a monoid, so without the coefficients. And monoid can be a monoid with and we can associate it to coefficients with rationals or coefficients with the F13 or whatever. So we have this algebraic structure, which is just the monoid, where we have only the multiplication of the power products. So as the LPP is actually a monoid LM. It doesn't know the polynomial ring. So in CoCoA5, we made things simpler. So the LPP is a polynomial, but in CoCoALib it isn't. So it is a PP monoid LM. As it is a PP monoid LM, I cannot easily multiplied with a coefficient, because if I multiply it by coefficient, it becomes a polynomial, but to become a polynomial must know in which polynomial ring it lives. You know that we do not have a global polynomial ring environment, and as the function use in CoCoA5 does. So we have to pass this information. That is the reason why we had to say which one was ring P. So we compute the least common multiple. The least common multiple is a monoid. And then we have to create the ring element, which is an element in a monomial, which is in the polynomial ring P, with coefficients 1 over LC of G, and with power products M divided by LPP of G. This multiplied by G. And for the second summand, we have a monomial in P with coefficient 1 over LC of H multiplied by M divided LPP of H. This is an exact division because M is the least common multiple of the two. And then this is multiplied by H. So I create this monomial here, I create this monomial here, and then I multiply one by G, the other one by H, which is what in CoCoA5 was simply m divided by Lm of G. Okay, that was the first surprise. So we learned that we have PP monoidal M's in CoCoALib. So we do operations on the pure monoid environment. The other object we need is the pairs. We want to store the pairs of indices. We can do it in many ways, but I decided to show you the class GB pair to make a class so that I can show you, one, how to make a class and how to use it, and to show you that quite often you want to make a class which hides the content inside because you might want to add more content, add more information that is inside, and you can control better what happens. So yes, there is a class called a template called pair in C++, but we are not using it. We make this little class. So the class GB pair has a public information, which is the functions you can call, and the private information, which is the data we store in it. It is always a good idea to have that the data is private so that you cannot access to it, you cannot modify it unless you call the specific functions. So when you create a class, you need to make it to show how you can construct one object of this class. And so we want to construct it, giving it two indices, making the pair. And you have to define a destructor, which is quite often the standard destructor that cleans up the memory for you. It's enough. You have to be extra careful if you have to manage memory, and then you might need to make a destructor that cleans up the memory better than the automatic version. Then we make two inline functions which allow me to see what's the first index in a pair and the second index in a pair, which are my two fields, my first and my second. The advantage of using these functions instead of just accessing the values is that in this way I can say that I want to take the first index and I'm not touching, I'm not modifying, I leave constant the value of the pair as it was. So I cannot be sure that I cannot modify, I have no way to modify the content of a pair. I don't want to modify it. This is a wonderful way to protect it. If you try to modify it, the compiler will say you cannot modify this because it's private or because you cannot call the function in this way. So the compiler will help you writing good code. I wanted to show you an example of a constructor, which does a little more than assigning the two values. For example, I can say that if the first index, I pass two indices, if the first index is bigger or equal than the second, then it's not a pair as I expect it to be inside my Grosvenor basis computation. So if by any chance I pass this, must be an error. So I want CoCoA to say, hey, stop here, because this pair is not good. You should not have in this algorithm a pair with the first index bigger than the second. So I throw an error, and this exits from all the functions calling it. Again, it is good to have some checks of this kind so that if there is an error, instead of going on and giving you at worst a result which is not the correct result, is it better to stop and say, there was an error, you shouldn't go on with this computation. So I also wanted to give you an example of this CoCoA throw error. And last thing is the function for printing, because this is a class I have to teach C++ how to print this class. And so this is the way of doing it. So I pass a string, which is usually cout, the usual channel on what we write, and the pair p, which is the letter used for polynomial ring. Too bad. So the operation lesson, which is the printing operation on the cout channel, on the out channel general. What do I want it to do? I want it to write a square bracket, then the first index, then a comma in the space, and then the second index and another square bracket, and then return out. So go to the channel on what we printed. So let's see how these work. So this is all the things I showed you in the previous videos. So here's the new part. So a new part, I can print. This is the G is the generators of my ideal, which had two polynomials, and I ask CoCoA to print the result of the S poly of G0 and G1, which actually should be sorry. I'm panicking because I'm recording. Okay, so the S polynomial of these two polynomials, and then I ask CoCoA to print the G pair 3 100 and G pair 103, which should give an error. So I compile, make, okay. You see how many errors I had before. X minus my G basis. Okay, I had an error, but so the first part is all the things we printed in the previous video, and this is the new part. So this is the list of the generators of the ideal, and this is the S polynomial. So which is I compute the least common multiple of these two leading product products. The coefficients are 1, so in this case everything is fine. So the least common multiple is x cubed. So I just do these polynomials minus x multiplied by this polynomial, and this is the resulting S polynomial. Okay, so I should do more tests, but I let you do it to write more tests for this function and see if I wrote any mistakes in it. And this is the pair I call G pair of 3 100, which prints as square bracket 3 comma space 100 close bracket. And I asked it to print the G pair of 103, which of course gives an error because it said CoCoA stop immediately if I get a pair which is not feasible. And this is the way CoCoA prints the error. This is all that part at the end of your file, which prints the all the error very carefully. So it prints what kind of error it is, non-standard because it's not classified, it's just a string. In the function gpair, in this file, in this line, and then it gives all the compilation informations of your CoCoALib, so that if you find some horrible errors inside CoCoALib, you can write to us, giving us this information and can investigate if there is a bug in CoCoA. Now we have all the ingredients to go on and implement the Grosvenor basis algorithm.